Hello, welcome back to my channel. Today we are going to start a new chapter, chapter 5, electromagnetic induction. So in this video, we are going to discuss on the summary for chapter 5. So for chapter 5, there are 5 subtopics. The first one is the magnetic flux, the second one is induced EMF, and 5.3 is actually a self-inductance. 5.4 is the energy store, and the last one is 5.5 mutual inductance. Okay, so we'll start with 5.1 first. Where 5.1 here we have the magnetic flux. Okay, so the magnetic flux is defined as the number of the magnetic field B passing through an area A. So equations that we'll use is B dot A, or we can write it as BA cos theta because this is a dot product. And the unit for the magnetic flux is the Tesla meter square, or we can use Weber. Okay, or Weber is WB, the short form for Weber. Okay, next we have the magnetic flux linkage. So magnetic flux linkage meaning that there are many turns. Okay, so magnetic flux linkage we can use NBA cos theta. Okay, where N here meaning that the number of turns. Okay, so this is the magnetic flux linkage, meaning that there's many turns inside. Okay, before we want to use these equations, please bear in mind that here we have the value for vector A. Okay, for vector A here, remember vector A always perpendicular come out from the plane. Okay, so this is how we determine the directions of vector A. So remember, vector A must perpendicular or 90 degrees from the plane. Okay, so for example, here we have vector B. Okay, vector B. Okay, vector A must come out perpendicular from the plane. Okay, so let's say this is our plane and this is our vector A. Okay, meaning that for the first case, this is cos 0 degree because A and B are parallel to each other. Okay, so next one is, let's say this is your B and the vector A must come up perpendicular or normal to the plane. Okay, so this is the angle or the theta between vector A and vector B. Okay, case 3, if let's say your plane is parallel to the magnetic field. Okay, so when the plane is perpendicular with the magnetic field, and remember vector A must come up perpendicular also from the plane. So this is our vector A. So for case 3, meaning that this is actually cos 90 degree or is actually equals to 0 because vector A and vector B are perpendicular to each other. So when they're perpendicular to each other, the magnetic flux is equals to 0. Okay, so this is case 3. Okay, next we go to 5.2, induced EMF. Okay, so induced EMF here we have to apply 2 laws. The first one is the Faraday's law, where Faraday's law stated that the induced EMF is directly proportional to the rate of change of the magnetic flux. So our equation, induced EMF, is directly proportional to the flux over dt. And the second law of induced EMF is Lenz law. Lenz law stated that the induced current flow in a direction that opposes the change in the magnetic flux. Okay, meaning that the Lenz law don't want any changes in the magnetic flux. If there is any changes, it will try to produce an induced current, okay, in such a way that to oppose the changes. Okay, so because of the word oppose, therefore our equation you must substitute negative. Negative meaning that it's actually oppose the changes of the induced the magnetic flux. Okay, so therefore equations for the induced current, EMF induced, is equal to negative and the flux over dt if let's say there is many turns. Okay, so this is the general equation for us for induced EMF. Okay, let's look at the diagram here for case 1. Okay, so for example, let's say this is the solenoid. Okay, solenoid, and this is our bar magnet. So initially, when the bar magnet and solenoid are put together, okay, so after that, when we push the bar magnet away from the solenoid, okay, so when you push the bar magnet away, meaning that if you follow the Lenz law, it will try to oppose the changes. Okay, so when you try to oppose the changes, okay, this is a south, okay, this is a south. So this one, when you away, meaning that it will try to pull back. So here will be north. Okay, and this is a south pole. Okay, so this solenoid will become electromagnetic, where it will induce the current, okay, try to oppose the changes. Okay, so when the bar magnet is away from the solenoid, it will produce an induced current. Okay, we must use right hand grip to determine where right hand grip. Thumb here is the north pole and the finger here indicate that the directions of the current. Okay, so if you grab the solenoid, you found that actually the current is flowing downward in this direction. Okay, it will flow in anti-clockwise direction. So if you insert a galvanometer, the galvanometer will deflect to the right. Okay, so it will try to attract back. Okay, case 2. Case 2, when the solenoid, okay, and the bar magnet is near to each other, when the bar magnet is into or move near to the solenoid. Okay, so when you want to near to the solenoid, okay, the sub pole here will try to near to the solenoid. Solenoid, if you follow Lenz law, it will try to, it will try to push it out. Okay, so how do it push it out? Meaning that this one will become south. South and south, it will repel to each other. So this is north. Okay, so again, you use right hand grip. The current now will flowing upward, will flow in a clockwise direction. So the galvanometer, it will reflect to the left. Okay. Okay, case 3. Again, the bar magnet is try to into the solenoid. Okay, so now if the north pole here, okay, this is a north pole trying to near to close to the solenoid. So the solenoid also, if you follow Lenz law, it will try to oppose. When you want to come near or into, it will try to push the bar magnet away. Okay, so here will become north. Okay, in order to push it out. Okay, so here the current, if you use right hand grip, the current will flowing downward. So it will flow in anti-clockwise direction. This one will be south. Okay, then we go to case 4. So now the bar magnet is away. Okay, the north pole is away. North pole here is away from the solenoid. Okay, so if this is a solenoid, we'll try to, okay, because north is away, so it will try to attract it back. This one will be south. Okay, so this current will flowing upward in clockwise direction. So the galvanometer, it will deflect to the left. Okay, because north and south, it will attract. When you want to away, it will try to attract you back. Okay, so this is the Faraday's law and Lenz law. There are 3 types of induced EMF. The first one is a straight conductor. The second one is a coil where B is changing or A is changing. And number 3rd one is a rotating coil. Okay, so let us start with the first one, a straight conductor. Okay, so if this is a conductor, initially there's no current flowing through the conductor. Okay, so when we move the straight conductor to the right, okay, it actually is a motion by the external force, meaning that we are pulling the conductor to the right. Okay, so this is what we call F applied. Okay, so when we have the force or the motions to the right, okay, we must use Fleming right hand rules, okay, to determine the directions of the induced current, where the thumb here represent the motion or the force applied, and the first finger here represent B, the magnetic field, and the second finger or the middle finger here actually is produce the I induced. Okay, so this is the value that we want to find. This is the directions that we want to find, I induced. Okay, so if we refer back to just now the diagram, okay, now B is cross meaning it's into the page, and the force applied here is to the right. The motion is to the right. Therefore, if you use Fleming right hand rules, okay, we can find out the directions of the induced current. Okay, so your B is into the page, the force applied is to the right, therefore it will produce I that acting upward. Okay, so I is induced, okay, and it is flowing upward. Okay, so when it's flowing upward, actually it will move in a anti-clockwise direction. Okay, anti-clockwise directions, because if let's say it move turn to the right, the complete is actually not a complete circuit. Okay, so therefore it will not turn to the right, it will turn in a anti-clockwise direction. Okay, so now when we say follows the Lenz law said that the induced current flow in a direction that opposes the change in the magnetic flux. Okay, so it will produce the I induced here, where the I induced direction is acting upward. Okay, so after we find the directions of the induced current, we need to go back to chapter 4. Okay, chapter 4, where we must use Fleming left hand rules to determine the directions of the magnetic force they produce. Okay, so we will go back to chapter 4, where I is going upward, B is into the page. Okay, so if you use Fleming left hand rules, B into the page, I is going upward, therefore FB, okay, meaning that the magnetic force will produce because there is a current inside the uniform magnetic field. Okay, so here automatically it will produce a magnetic force that is acting to the left. Okay, so if you follow Lenz law, initially when you push the conductor to the right, okay, so this is what we call F applied. Okay, and this is the motion by the external force. Okay, so if you follow Lenz law, it will produce an induced current, where the induced current for this case is actually acting upward. Okay, so why is acting upward? Because they want to produce a magnetic force that is opposed, that is acting to the left. Okay, oppose the F applied. Okay, so equations that we will use for a straight conductor is L B cross V, or we can write as L B V sine theta, because it is a cross product. okay, where the angle here is between vector B and also vector V. Okay, so this is the first equations for induced EMF. Okay, next we will go to the second part where a circular coin. Okay, for number one, when B is changing. So initially, if you observe here, there are 4 lines of the magnetic field line that enter the coin. Okay, after that, when we increase the magnetic field line, which is entered to the coin, now already have 7 lines, meaning that B is increasing. So when B increase, if you follow Lenz law state that it don't want any changes. So it will try to oppose. Okay, so how can it try to oppose? It will produce a induced current. Okay, so induced current here, it will move in clockwise direction. Okay, why in clockwise direction? Because it want to produce B that acting into the page or acting downward. Okay, how can we determine the directions of the induced current? We must use the right hand grip, where thumb here represent the current and the finger here is represent B. Okay, so you grab the wire where your finger must into the inside the wire. So when you grab, okay, meaning that when you grab, this is the thumb here and your finger is put inside. Okay, put inside the wire. Okay, so that it will show that the B, okay, the directions of the finger actually shows the directions of B is acting into the page. Okay, so the finger or your thumb here represent the directions of the current, where the directions of the current flowing in clockwise direction. Okay, so the equations that we will use for B changing is EMF equals to negative NA dB over dt cos theta. Okay, so from where this equation actually is from the equation, the Faraday's law, where negative EMF equals to negative N d flux over dt, where the flux here, we also can write it as AB cos theta over dt. Okay, so now since B is changing, so we just differentiate dB over dt. Okay, we will take final minus initial. Okay, next, A is changing. So if you observe here, okay, the area here, A1 and A2, of course A2 become bigger. Okay, so now A is changing, the area is changing. Therefore, the equation for the coin when A is changing will become negative NB dA over dt cos theta. Okay, so we differentiate dA over dt. Okay, so usually cos theta here for this case is actually parallel. Okay, so usually it will equals to 1. Okay, it's cos 0 degree or equals to 1. Okay, next is the rotating. Okay, so EMF for rotating, N B A omega sine omega t. Okay, so from where we'll get this equation, where it's actually from negative N BA cos omega t over dt. Okay, so since this is a rotating case, meaning that the angle of the coin will always changing due to the rotating. Therefore, we take out B and A because it's constant, and we differentiate cos omega t over dt. Okay, so if you differentiate cos omega t, we will get sine omega t, copy back, and then we differentiate omega t, we will get omega. Okay, so from here we will get the okay, and then we differentiate cos omega t, of course we will get negative, negative now become positive. Okay, so this is the equation for a rotating coin. So let us look at the first diagram. Okay, let's say this is number 1, number 2, 3, 4, 5. Okay, so we look at number 1 first, where initially A is at the bottom. Okay, so our magnetic field B is to the right, and the vector of A is also perpendicular to the plane. Okay, it's to the right as well. Therefore, both of them are 0 degree. So sine 0 degree, you will get 0. Okay, so this is our first point. Second diagram, B is to the right and the vector A is actually going downward. Okay, so both of them are 90 degree. So sine 90 degree actually equals to 1. Okay, so we continue. A now shift to at the top of the loop. Okay, so similar, B is to the right, and now the vector of A is to the left. Okay, therefore they are 180 degree. So sine 180 degree is actually equals to 0. Okay, so this is the point. Okay, so the fourth diagram is now the A already going downward. Okay, so vector B is still the same to the right. Now vector A will going perpendicular to the coin, is going upward, vector A, and both of them are 270 degree. Okay, so 270 degree sine 270 degree, actually you will get negative 1. Okay, and the last one is A, you will go back to the bottom. Okay, so it will going downward. So B still the same to the right. Vector A will go back to the initial point. Yeah? So both of them actually is 360 degree. So sine 360 degree actually we will get back 0. Okay, so what can we observe here is at the end here we will get a sine graph. Okay, we will get a sine graph. Okay, so this is a sine graph where we will get at the end. Okay, so that's why the equation is NBA omega sine omega t. Okay, this is a sine graph. Okay, next we will go to 5.3. Okay, 5.3 is the self-inductance, where self-inductance meaning that the productions of the induced EMF due to the change of the current in the circuit itself. Okay, so here we have two cases. Case number one is when the power supply is on. Okay, so when we switch on the power supply. So when we switch on the power supply, I is increasing. Okay, so initially there's no current. Okay, after that, when we on the power supply, the current will flowing in the coil. Okay, or in the solenoid. Okay, so if you follow Lenz law, okay, Lenz law stated that it will try to oppose the changes. So when you want to increase the current, it will try to reduce the current. Okay, so meaning that it will try to reduce. Okay, the blue color one is trying to reduce the current that it's increasing just now. Okay, so meaning that it will flow the current induced, it will flow in clockwise direction. Okay, it will flow in clockwise direction. Okay, and just now the current when increasing, it will flow in anti-clockwise direction. Okay, so already opposed. Okay, case 2 is when we off. Okay, so when we switch off, okay, there is also a changes because the current already reduced. Okay, so initially the current is flowing in anti-clockwise direction. Okay, so when we off meaning that the current is reduced, becomes 0. Okay, so if you follow Lenz law, okay, Lenz law stated that it will try to oppose the changes. Okay, so it will try to oppose, okay, meaning that when your I is reducing, it will try to increase the current. Okay, so what we do is it will try to maintain back the current. Okay, it will try to maintain back, meaning that it will flow similar, it will flow in anti-clockwise direction. Okay, because it's trying to maintain back. Okay, so for this case, why we have induced EMF is because of, okay, it's because of there is a changes of the current, whether the current is increased or the current is reducing. So the equation for the induced EMF for the self-inductance equation, we can write it as EMF equals to negative L di over dt, where this is because of there is a changing of the current. Therefore, L we can write as EMF over di over dt. Okay, and since EMF also equals to N the flux over dt, okay, and for self-inductance is also equals to L di over dt. So if we cancel off the t, okay, therefore we will get N flux equals to Li. Or if you rearrange back, L will equals to N flux over I. Okay. Next, if let's say this is a coin, okay, so we can derive it where L equals to N flux over I, where flux is B A over I. Okay, so for a coin, B for a coin, we can write it as mu naught Ni over 2R. Okay, so we can cancel off the I. Therefore, the equation for the coin, the self-inductance, is equal to mu naught. Okay, we have 2N, so it's N squared A over 2R. Okay, if let's say this is a solenoid, meaning that mu naught Ni over L. Okay, therefore for solenoid equation will become mu naught N squared A over length. Okay, so this is equation for a solenoid and a coin. Okay, and the unit for the self-inductance is Henry, or we can use capital H. Okay, so this is self-inductance. It will produce EMF, okay, because of there is a changing of the current in the circuit itself. Okay. Okay, next we go to 5.4, energy store. Okay, energy store here is the inductor is an electrical component that use self-inductance to store energy in the form of magnetic field. Okay, so it will store energy in the form of magnetic field. Okay, for chapter 1 or for chapter 2, the capacitor, it will store energy in the form of electric field. Okay, but for self-inductance, for inductor, it will store the energy in the form of magnetic field. So the equations for the energy store, U is equal to half Li squared. Okay, and the unit for the energy store is joule. Okay, or capital J. Okay, next 5.5. mutual inductance. Okay, mutual inductance is the production of induced EMF, similar like just now, but this induced EMF is due to the change of the current in the neighboring conductor. Okay, so this is because of the neighboring conductor, the current in the neighboring conductor changing, so it will induce EMF. Okay, so here we have two coin 1, which has the battery, okay, or the power supply, we call it as primary. Okay, the one with the galvanometer, we call it as secondary coin. Okay, so if you observe here, the battery, okay, initially the current is flowing, for example, if flowing in the clockwise direction, so the current is flowing in clockwise direction. Okay, so initially, if let's say before we on, there's no current. So when we on the power supply here, coin 1, there is a current flowing through. Okay, so meaning that I is increasing. Okay, so when I is increasing, it will produce a magnetic field that will go to coin 2. Okay, so how we know the magnetic field is out from the coin, meaning that we need to use, okay, so we can use the right hand grip. Okay, still remember right hand grip where the thumb here represent north and the finger here represent the directions of the current. Okay, so if we grab, the current is flowing downward, so this is a north pole, this is a south pole. Okay, so when north pole, the magnetic field line, it will out from the north pole. Okay, and it will go to influence the coin 2. Okay, so coin 2. Okay, so coin 2 is what we call secondary coin. Okay, it will try to oppose the changes, meaning that when the magnetic field try to into the coin 2, it will try to push it out. Okay, so it will try to push it out. Okay, so when it push it out, meaning that here must be north, this side must be south. Okay, so again we use right hand grip. Okay, if this is a north, meaning that your finger here, okay, if you grab the coin, meaning that this is north and the directions of the current is acting upward. Okay, so it will acting upward. Okay, it will flow in this direction. Okay, it will flow in this direction. Okay, therefore the galvanometer initially at 0, it will deflect. Okay, it will deflect to the right. Okay, showing that induced current is produced. Okay, due to the changing in primary coin. Okay, so I1 changing, so it will produce I induced in a secondary coin. Okay, okay, so the equation for the induced EMF for the mutual inductance is negative M di over dt. Okay, so because of the changing of the current by the primary coin. Okay, or we can write it as EMF also equals to negative M the flux over dt. Okay, therefore, okay, if you compare these two, M di over dt equals to N the flux over dt. So we cancel off the t, we will get M equals to N1 flux 1 over I2, or we can write N2 magnetic flux 2 over I1. Okay, so meaning that for the first equation, N1 flux 1 is produced because of there is a changing of current I2. Okay, similar, if you want to use the second equation, N2 flux 2 produced because of there is a changing of I1. So actually they are both mutually influenced by each other. Okay, if I say M for the solenoid, okay, we can also use the equation mu naught N1 N2 A over length. Okay, so this is subtopic 5.5 mutual inductance. Okay, and this is the equations that we will use. Okay, so that's all for this summary. See you on next video. We will continue.